This video is part of a free course. If you want to learn more about PID controllers in an easy-to-follow format, head on over to realpars.com, where you can sign up for this course, as well as several other courses on PLC programming and other topics related to industrial automation and robotics for free. You can find the link in the video description as well. In this video, we're going to look at the effects of proportional-only action on a flow control loop. Proportional-only control is the simplest of the PID controller actions, but is seldom used in industrial production processes. The problem with P-only control is something called offset. In this video, we're going to explain offset and show you how and when it occurs. The controller in our loop is typical of most controllers. We can adjust the set point and switch between auto and manual. In manual control, we can adjust the controller output to the exact amount we want. Our flow loop has a pump to move our process fluid. We can turn the pump on or off, which will be very helpful for observing PID responses in static and dynamic conditions. Okay, let's kick things off with a look at our flow control loop PID. The flow is manipulated by the pneumatic final actuator FCV200. The controller FRC200 produces an electrical signal that operates the pneumatic final actuator through a current to pressure or I to P converter FY200. The differential pressure transmitter FT200 sends an electrical signal representing the flow rate to the controller. And now, let's look at an animation of the flow loop in operation. Okay, let's start investigating the effects of adjusting the amount of proportional action on our flow loop. The controller output range is 4 to 20 milliamps, representing 0 to 100%. When the process is stable, the controller output will be at some value between 4 to 20 milliamps. The process variable is also represented by a 4 to 20 milliamp signal from the flow transmitter. This signal represents 0 to 100% of the process variable. Alright, now that we know how the flow loop operates, let's move on to proportional control. So what is proportional action? The controller's job is to ensure that the process variable is the same as the set point. The controller is always looking at the difference between the set point and the process variable. This difference is often referred to as the error. Proportional action is an amplification of the error. This proportional amplification has no units and often is referred to as gain. This amplified result is added to the current controller output. Okay, now we have a simple math formula. New controller output equals previous controller output plus gain multiplied by error. Let's look at an example of proportional action and how that math formula applies. We'll start with the pump off. With the controller on manual, we'll set the output to 50%. We'll set the gain to 1. Now, let's set the controller to auto. With the pump off, the PV, or process variable, will be 0. Watch what happens when we change the set point from 0% to 10%. The set point change of 10% produced a 10% change in controller output. Why? The controller output, or CO, changed by 10% from 50% to 60%. Earlier, we said that proportional action results in a change in controller output based on the simple math formula. Controller output equals CO plus gain multiplied by error. Our set point changed from 0 to 10%, which produces an error of 10%. The gain is set to 1. Because the gain is 1, the proportional action will only add 10% to the controller output. The controller output was at 50%, so adding the proportional response will move it to 60%. Let's try it again, but this time we will increase the gain to 2. This time the CO changed from 50% to 70%, which is a 20% change. Why? Because the gain is now set at 2. Therefore, the proportional action will add 20% to the controller output. Keep in mind that the pump has been off for both of our experiments. With the pump off, we have no possible change in the process variable. Therefore, our proportional action is acting on a static condition. Once the pump starts, we are in a dynamic environment, and variables are changing with time. Let's turn the pump on and watch the proportional action dynamic response. We start with the process variable at the setpoint value of 75%. When we introduce a setpoint change to 65%, the controller initiates proportional action and attempts to change the process variable to move to 65%. But the process variable only goes to 69% and stays there. A proportional-only controller does the job expected of it, at least until a disturbance, process variable, or setpoint change happens. In the beginning, the process variable equals the setpoint and the error is 0. The process variable is stable. A process disturbance will cause the process variable to change and the controller will act. Unfortunately, the process will recover back to a condition of stability, but not with the process variable at the setpoint. The difference between process variable and setpoint is called offset and occurs in proportional-only controllers. In our next video, we'll show you how adding integral action will help bring the process variable back to the setpoint, thus eliminating the offset. If you want to learn more, you might want to review our other videos called PID Controller Explained, How to Tune a PID Controller, and What are PID Tuning Parameters. You can find the links to these videos in the description. Okay, let's summarize what we've discussed. The controller's job is to ensure that the process variable is the same as the setpoint. The controller is always looking at the difference between the setpoint and the process variable, and this difference is often referred to as the error. Proportional action is an amplification of the error. Proportional amplification has no units and often is referred to as gain. A simple math formula for controller output after proportional action is controller output equals CO plus gain multiplied by error. A proportional-only controller will result in an offset condition after a disturbance or setpoint change. Want to learn PLC programming in an easy-to-understand format and take your career to the next level? Head on over to realpars.com.